Greetings, Misala. My name is Felicia of Group 4, and today, along with my teammates Kalyani, Lambert, Putri, Tadeus, and Wilson, we will be presenting our IOL project, that is the design and analysis of experiments in cancer treatment based on their treatments and the age group of patients. First of all, what is cancer? So, cancer is an umbrella term which refers to a rapid and uncontrollable creation of abnormal cells, which usually spreads from one part of the body to other organs. Here, you can see a list of most common cancers and the most common cause of death by cancer. So, to summarize, cancer cells are different because they grow without the brain's instructions and they don't die by the brain's instructions either. They can also fool our T cells and mess with our immune systems instead. And most dangerous of all, they can mutate, which can complicate the cancer. Several causes of cancer are, first of all, cell division error. Second of all, they could be inherited from the parents or ancestors. Third, DNA abnormality from external factors such as smoking. And finally, old age. The thing that makes cancer so terrifying is that cancer does not have a cure that truly gets rid of it. Medical experts can only suppress it using several methods, most commonly chemotherapy, radiation therapy, and surgery. Cancer is categorized into stages, starting with stage 0, where cancer cells have emerged in a certain organ, and ending with stage 4, where the cancer cells already spread to other organs.
So right now I'm going to explain about inverse normal. So what is inverse normal itself? So the inverse normal refers to the process of finding the value of a random variable x in a normal distribution, given its cumulative probability. This is often used in statistics for problems involving percentiles, confidence intervals, hypothesis testing, and many more. The normal distribution itself is a continuous probability distribution characterized by its mean and standard deviation. Its cumulative distribution function calculates the probability that the random variable x is less than or equal to a specific value of x. And right now, I'm going to discuss about the concept of inverse normal. So the inverse normal function works in the opposite way of the CDF. Instead of computing the probability from x, it determines the x value corresponding to a given cumulative probability p. So below here, it is the rule for the concept of inverse normal. And this is the steps to use inverse normal. The first thing that we need to do is to define the parameters. We need to get the value of mean, standard deviation, and lastly, the cumulative probability for which unit x. And the next one is standardized problem. We can convert the normal distribution to the standard normal distribution using the formula below. And the next one is find the z-score value. Using an inverse normal table, statistical software, or a calculator to find the z-score corresponding to p. And after we successfully obtain the z-score value, we can move to the next step, which is transform back to x. And we can calculate the x using the formula below. And this is the applications of inverse normal. The first one is percentiles. We can find the value below which a certain percentage of data lies. And the next one is critical values. In hypothesis testing to determine the cutoff values for rejecting or failing to reject the null hypothesis. And the last one is confidence interval, determining the bounds of a confidence interval for a given confidence level.
Now I'm going to explain about what is ANOVA. ANOVA, or usually called analysis of variance, is a statistical method for analyzing differences among group means. It is especially useful for comparing three or more groups to identify significant differences. For two groups, ANOVA results are equivalent to a t-test. Next, I'm going to explain about concepts and components of ANOVA. So here you can read the detailed explanation of each concepts and components of ANOVA. So first, there is no hypothesis. Second, there is alternative hypothesis. Third is between group variability. Fourth is within group variability. Fifth is as statistics. And sixth is significance level. So next is advantage of ANOVA. So first, ANOVA reduces the risk of committing type 1 errors when comparing multiple groups. So here ANOVA evaluates all group means simultaneously under a single statistical test. Second, ANOVA is versatile and can analyze more than just simple group comparison. Third, ANOVA provides a single S statistic to summarize whether the significant differences exist among groups, making it computationally efficient and easy to interpret. So next is ANOVA table. As you can see here is the ANOVA table, where N is the total number of observations, K is the total number of groups, for example like A, B, C, and there are formulas for SSD and SSW. So first you need to set the hypothesis. For example, the null hypothesis is assume that all group means are equal. And for the alternative hypothesis, assume that at least one group mean is different from the others. Next, you should count the table using the formula thus. And for the conclusion, reject the null hypothesis if F statistic is bigger than the F table.
RCBD, here are the explanation. It is similar to ANOVA 2A, but instead of using between and within groups, we use treatment and blocks as the replacement. Here are the components from RCBD, which are consists of blocks, treatments, randomization, and of course replication. The advantage of RCBD, we have controls for inherent variability within blocks, enhanced statistical precision in detecting difference among treatments, reduce the experimental error caused by extraneous variables, and lastly, suitable for situation where heterogeneity exists in the experiment unit. We have the design layout RCBD. First of all, we randomly assign the treatment within each blocks, then ensure every block has all the treatment to maintain the completeness. Then each group we contain all the treatments and patients are randomly assigned to treatments within their age groups. We can see it right here. Then how to solve it? First of all, we of course declare the hypothesis, which are null hypothesis and alternative hypothesis right here. Then we use a two-way ANOVA. Then we have the formula here. We at last we got the F value. We compare the F value we got from the F table. If it is higher than if stat is higher than table, we reject H sub O. Likewise, the opposite is true if it's smaller.
Now, I'm going to outline the data we use to analyze cancer. From data set with the cancer as a point of interest, I will insert the rows where the disease name is cancer and delete the others. Regarding the size of the data, that consists of 25,160 rows and 22 columns. Regarding data quality, we check that there are no null values, no outliers in the dataset, which indicates that the data is clean. During processing, we did further transformation to the data, basically changing the treatment type and age as categorical variables and transforming the recovery variable. Next, I will explain the assumptions testing that we conduct regarding heteroscedasticity, autocorrelation, and normality. For heteroscedasticity, the bridge percentage thought of p-value of 0.505 is greater than 0.05, meaning there is no evidence of heteroscedasticity. So the residuals have constant variance, which means they meet the assumptions of homoscedasticity, or fail to reject hypothesis null. Next, we use the Durbin-Watson test to check for autocorrelation. Durbin-Watson statistic is 1.9927, which is close to 2. That means there is no significant autocorrelation in the residual. This is supported by the p-value, which is 0.2823 and is greater than 0.05. So the residuals are not autocorrelated, which means they meet the assumptions of fail to reject hypothesis null. Then, in the homogroup Smirnov test, the p-value is smaller than the alpha of 0.05. That indicates that the residuals are not normally distributed. So this violates the assumption of normality or reject the hypothesis.
Okay, so right now I'm going to explain about the transformation that we did inside the dataset. So first of all, we changed the age and treatment type variables to categorical types symbolized by numbers. So the age is changed from the numeric to categorical, and the treatment type is changed from string to categorical. And we also transformed the recovery rate variable, which is the y variable, with inverse normal to normalize the data. So here we can see the histogram before the transformation. So it indicates that the distribution may be uniform. And after we did inverse normal transformation, the histogram shows that the distribution is already normal. So here's the ANOVA model that we made. So the ANOVA equation is y equals 6.018e minus 0.7 minus 0.012 medication plus 0.011 surgery plus 0.008 therapy minus 0.007 vaccinations plus the error. So since the treatment types are categorical variables, they're transformed into dummy variables. So for example, if the treatment type is medication, then the surgery, therapy, and vaccinations coefficients will be 0, and the medication coefficient will be 1. So here we have the summary of the ANOVA table. We have the treatment, the sum of square as 3, mean square as 0.887. The F value is 0.87, and the P value is 0.45. And for the residuals, the sum of squares are 25,138, and the mean square is 0.999. So the p-value of 0.454 indicates that there is no significant effect of treatment on recovery. Since the p-value is larger than the alpha of 0.05, we fail to reject the null hypothesis, meaning the different treatments do not significantly impact the recovery rate. The next one is the RCBD model. So the RCBD model, for the block, we have the age group, and for the treatment, we have the treatment type. So here we have the summary of the RCBD. For the treatment, the sum of square is 3, the mean square is 0.87, F value is 0.87, and the P value is 0.45. And for the block, we have the sum of square as 3, mean square as 0.83, F value of 0.83, and the P value of 0.47. And for the residuals, we have the sum of square as 25,135 and the mean square of 0.99. So the p-value of 0.47 for block indicates that the block variable also has no significant effect on recovery. This means that the block factor, which was likely included to control for variation, does not contribute significantly to explaining the recovery rate. So in a conclusion, neither treatment nor block has a significant effect on the recovery rate, as evidenced by their high p-values, which is higher than the alpha of 0.05. Okay, so here are the contributions in this AOL, and that's all. Thank you for listening.